This conference will now be recorded.
Very good evening, students. We are discussing electric potential and related things. So today, with a brief recapitulation, we'll start today's class and we'll do few numerical problems on electric potential. Okay. So look, in the last class we had discussed electric potential due to a point charge. By the way, what is the definition of electric potential? We had done that day the work done per unit charge. Okay, what was work done? Work done was the field, you know, electric field into Q, that is the force, and actually that was kind of work done means change in the potential energy. Okay, change in potential energy. U2 minus U1 or U1 minus U2 divided by K. So that was the thing. So for a point charge, suppose there is a point charge Q here, and we want to calculate electric potential at some distance R. This is point P. Okay. So what will be the electric potential? We had already learned that can be written as, so it is also a function of position. So okay, so this electric potential at this point P due to point charge will be Q by 4 pi epsilon naught R. Okay. Suppose you have, so this is due to a point charge, single point charge, due to a point charge. Suppose there are multiple point charges, then how do you calculate that? Okay, suppose you have multiple point charges or a system of charges, then in that case, the potential should be written as one over 4 pi epsilon naught. This is common. Then summation over Qi, the point charge, and the distance here in the denominator where it's situated. Suppose this is x, y, z. So x, y, and z. Some particle has like some charge particle. Suppose here there is a point. Okay, so here is the point. I have to calculate the electric potential due to this charge Q1 here, then Q2 here. This is suppose the position vector R1. Okay, suppose the position vector is here R1. This is R2. This is Q2. Okay, like this I have to, suppose this is Q3, position vector R3. So I have to calculate the electric potential due to the charges at this point position P. Okay, so at the origin, say. So in that case, how do you write that? So just break the summation or expand the summation. Q1 by 4 pi epsilon naught R1 plus Q2 by 4 pi epsilon naught R2 plus Q3 divided by 4 pi epsilon naught R3. Okay, if this is the case, this is the case when these distances are different from all the charges. Okay, this point P or origin say O, if this point is different at different distances, like A from this Q1 is R1. So if the distance between the charge and the point where we are calculating electric field, sorry, electric potential is different, then this is the formula. But suppose all the charges are at same distance, all the charges are at same distance. Here Q1, here Q2, here Q3, here Q4. I have to find out the kind of square. I have to find out electric potential due to all the charges at this point O. So how do you write that? In that case, this electric potential could be written 1 by 4 pi epsilon naught. Suppose the distance is R0 from each of them, R0. Okay, so R0, and this is summation of all the charges. Okay, or I can say net charge Q net divided by 4 pi epsilon naught R0. So this will be in case of a system of charges when all the charges are at the same distance from the point where we are calculating electric potential. Okay, we have taken one example in this case. Look what will be the electric potential. So what is the electric potential? Due to due to a system of charges, point charges, system of point charges placed so what is the electric potential due to let us say directly due to the point charges placed at the vertices of the square of side A. What is the electric potential at the center of the square? Let us say at the center of the square. Center of a square due to point charges placed at the vertices of the square of side A. So all the sides are A. So in this case, you look this point at the center, we have to calculate the potential. So this distance, suppose this is R1, this is R2, this is R3, this is R4. So all this R1, R2, R3 and R4 are equal from the center. Okay, so for this case, you can just apply this formula, potential at the center. Okay, at let us say this is O, at O is given by Q net charge divided by 4 pi epsilon naught. Suppose the distance is r in the sense, in this case, if it is A, we know this will be root 2 root 2a divided by 2. So this will be a by root 2 actually. A by root 2. So what is q net? So q net is sum of all the charges. See here 4, then minus 2, plus 2, minus 4, all are microcoulomb unit. So this is net charge 0. So what is the potential at the center? See, potential is 0 at the center because net charge is 0. So net charge is 0. So that's why the electric potential at the center of the square will be 0 due to the point charges. Okay. All right. Now we have learned due to point charge and system of point charges. If suppose the charge is not discrete, okay, how to calculate? Now my agenda is let us just forget about this figure now. How to calculate electric potential for continuous charge distribution. Sorry. Continuous charge distribution. Okay, so this is my agenda now. If suppose there is a continuous charge distribution of charge delta Q, so in that case, this could be written as integration. See, integration dq 4 pi epsilon naught here this. Okay, this is the formula we have to use. So dq is the elementary charge distribution, and then you have to integrate with the proper limit. So this is the formula. We will just use this to calculate electric potential for a ring, charged ring. Okay. So here you can see a charge q is uniformly distributed over the circumference of a ring, pass A, and second is non-uniformly distributed in B. So when charge is uniformly distributed, in that case, how to calculate electric potential? We know that how to do that, isn't it? Let us try to solve. See, in this case, we have to take electric field. Generally electric potential we have to calculate. Let us say this is dq integration 4 pi epsilon naught. Okay, now since this charge q is uniformly distributed, then we can calculate electric potential at a distance, some distance x, say, and the ring has radius r. Okay, if I consider a small element of length element of this ring which has charge q, So for that case, at any point P, which is the x distance away from the center of the ring, what will be the electric potential? That will be as a function of x, as a function of x. So see, that is this is suppose r, and this is capital R, as you know, radius of the ring. So in that case, you know what you have to do. You have to calculate d cube by 4 pi epsilon naught r. Okay, you have to calculate first that, and as you know, we will have similarly we'll have for this part as well. So if you write this dq, see this, we have to do the integration first of all. What is dq? Since it is on the circumference, actually we can write dq is the total charge q by 2 pi r. This is the charge per unit length into, suppose that has this some length dl. Okay, dl, that we can write. Okay, so this is r. So dq will be actually this one. This will be q by 2 pi r. So this is charge per unit length into dl. If this has length dl. Okay, so q by 2 pi r into dl. So by doing this, we have to integrate this dl over dl actually. Okay, or you can just take the sum of that, summation over that. Okay, we can take summation over this also, or we can just do the integration also. So first of all, let me tell you this as summation itself. So summation, you have to just sum over this, because this distance is fixed, right, from each and everywhere. So look, in this case, this r is square root of r square plus x square. Okay, so this is also fixed quantities. R is the radius, that is a constant value, and this x is the point where we have to calculate the potential. So far so good. So we can write, so dq, in place of dq we can write q by 2 pi capital R into dl. Okay, we have to take sum of that, divided by 4 pi epsilon naught r. Okay, now this thing, okay, so this r we have already written r square plus x square. Okay, now if we do this, so dl will be, again, if we take the summation, see q by 2 pi r, let this be there, and summation over dl divided by 4 pi epsilon naught square root of r square plus x square. I think I'll take the next page as well. So the potential at any point P on the axis will be q by 2 pi r summation over dl divided by 4 pi epsilon naught square root of x square plus r square. Okay, now this sum will be again 2 pi r. So 2 pi r 2 pi will be cancelled. So q by 4 pi epsilon naught square root of x square plus r square or r square plus x square, whatever you say. So this will be the electric potential due to a ring. Okay, this is the electric potential due to a ring. We'll take up one simple example. Okay, then it will be clear to you. So here is the simple example. We'll just take here. Suppose a charge Q is equal to 10 microcoulomb is distributed uniformly over the circumference of a ring of radius capital R is 3m. Placed in the xy plane, you see this horizontal plane is said to be xy plane here. Okay, and with its center at the origin here. Find the electric potential at P. That P point is on the z axis. On the z axis. So this is kind of axis of the ring. So how do you calculate that? As you know, how to do that? So see, we have already seen this is q by 4 pi epsilon naught r0. See here r0 as you see in the figure, and that r0 is so q by 4 pi epsilon naught r square plus x square. This is the thing. So what is x? X is here 4 meter. What is capital R? R is 3 meter. So what is the potential at P? So potential at P, that is q by 4 pi epsilon naught square root of 3 square plus 4 square. Okay, so this is, see, we just put the value of 1 by 4 pi epsilon naught and q. 1 by 4 pi epsilon naught will give you 9 to 10 to the power 9. Just we are taking the value, and q is 10 into 10 to the power minus 6 microcoulomb. So that's why. So what is this here? So 9 into 10 to the power 4 divided by this will be 5. Okay, so it will be actually 1.8 into 10 to the power 4, and obviously this will be volt in volt, or 18 into 10 to the power 5 you can write otherwise. Okay, how much you can write? 1.8 into 10 to the power 4 volt, or 18 into, so 18 into 10 to the power 5 volt. I'm sorry. 18 means we are multiplying, so you have to divide also. This will be 33 volt. All right. So this is one simple example. Now we'll go to the next. Okay, let us just discuss this result a little bit. Potential due to, see, electric potential due to a ring, how it varies with distance. So how does electric potential due to a circular ring vary with the distance along the axis, along its axis, okay, distance along its axis. That means, see, when I have a ring, this is the axis of the ring, and suppose the distance, which is r, from the center of the distance, sorry, center of the ring, I have to calculate the electric field. We have already, sorry, electric potential. We have already seen that is q by 4 pi epsilon naught and r. Okay, and this r we had seen. Sorry, this, let us say this is x distance p. So this is r. This is capital R. That is what we have seen. So V of R is equal to Q by 4 pi epsilon naught square root of R square plus X square. Okay. Now, see this point, we can see V of, see on the axis, when distance is changing, suppose uh, this X is 0. That means what is the potential at the center? So that will be Q by 4 pi epsilon naught R. So what about this, as so this is the actually maximum value at the center, the electric potential, this is V0, say. So this is the value here, as you see here, and on either side, on either side, when the distance increases, then the potential due to the ring decreases. So if I have a ring like this, so electric potential vary like this. Okay, at the center it will be maximum, and on either side the electric potential will be decreasing. So this is actually kind of a bell-shaped curve or Gaussian curve. All right, so this is the thing. Now we'll learn how to calculate electric potential on the axis of a uniformly charged disk. On the axis of a uniformly charged disk. So how to calculate that? See, we know the basic formula for continuous charge distribution. In this case, this is X. So potential, electric potential for a continuous charge distribution, we know this is dq, and we have to take the summation of that, or integration we can do. So what we can do, dq divided by 4 pi epsilon naught x integration, we have to do the integration. Okay, okay. So in this case, suppose let us consider, so this is actually disk, means everywhere there is charges. Okay, everywhere there is charges. Disk. Okay, so everywhere there is charges. That's why we should not just consider the circumference, we should consider the whole disk. So we can consider, okay, we can imagine that the disk is made of made of a large number of a large number of a large number of circular strips, circular stripes. Okay, so here we have just considered such a stripe of radius r and thickness dr, but in this case it is not a just circle. Circle does not have, or ring does not have any thickness as such, but we are taking a stripe which has a thickness here dr. Okay, we are taking a stripe which has thickness, and in this case you have to consider the surface charge density sigma. Sigma, which is the total charge distributed over the disk divided by the area of the disk, that is pi r square. Okay, so this will be, if capital R is the radius, so that is the sigma. Now we have considered such a circular stripe of thickness dr. Okay, so if we want to calculate electric field, sorry, electric potential due to this stripe at distance x from the center, what will be the value? We have already discussed circular. In case of circular ring or a ring, in case of ring, what we get 1 by 4 pi epsilon naught into dq by this distance. Okay, the distance from the ring, that is this one. This is smaller and this is x, so this is x squared plus small r square. Okay, so this is the electric potential for this stripe. Okay, so that is dV. Now see, we have to find out dq to find out the total. See, if I want to find out total electric potential due to the whole disk, then I have to integrate this. Okay, I have to integrate this one. So for that, we need to first find out what is dq. Let us first find out what is dq. dq, as you know, this will be a surface charge density. So dq is sigma into the area of the stripe. Area of the stripe. So sigma, what is the area here? For this stripe, it is 2 pi r into dr into sigma. So this is actually the area of the stripe. All right, so I can write it dV. In place of dV itself, we can write 2 pi small r dr into sigma divided by 4 pi epsilon naught whole into this into r square plus x square. So now we have to integrate this over dr. So to get the electric potential, therefore or electric, simply electric potential, potential at P due to the whole disk This is given by V is equal to integration 0 to R into dV. Why you have taken this limit 0 to R? I'll tell you here. See, if we write the dV, then it will be clear to us. 0 to R, 2 pi small r dr divided by, here there will be sigma term, divided by 4 pi epsilon naught square root of r square x square. Okay, this is the thing. Now, if I just take these things out, see 2 pi, here 2 sigma, r dr will be there. We'll check from here. So sigma by 2 epsilon naught. Sigma by 2 epsilon naught, integration 0 to r. See, this small r is actually the radius of the circular stripe. If we take the limit 0 to capital R, that is the radius of the whole disk, then it will be the potential due to whole disk itself. R dr divided by this. Now this part we have to do the integration. So how to do this integration? This is also a typical integration. So let us say this is I. Let us not worry about the limit for the time being. So I is integration r dr divided by square root of r square plus x square. So this integration we have to do, and what is the value we have to find out. See, we have to do a simple, very simple substitution. So we know r is the variable, so we have this r is equal to, if I write x tan theta, look what we get, tan theta. Then dr will be how much? Dr will be x is not a variable. You can see that x is the distance from the center, that is fixed actually. Only thing is varying is r. R is the radius of the ring. Sorry, disk. So this is 10 sec square theta d theta. Okay. Now we have got dr, and what is the value of r? So r is x tan theta. Sorry, r is x tan theta. So dr is how much? X sec square theta d theta. What about here? Here we get x square plus x square tan square theta. Okay, so you know this trigonometric identity, sec square theta minus tan square theta is equal to 1. And see this 1 plus tan square theta, then what it will be? Tan square theta means this is x square theta. Okay, so I'll get here, so x square, if I take common, so x tan theta, sorry, this x square tan theta sec square theta divided by, this is x, and 1 plus tan square theta means sec square theta, so sec theta will be there. So 1 sec, sorry, 1 only sec theta will be there. So 1 sec theta will be cancelling another sec theta in the numerator, and 1x will cancel other x. So we'll get, look what we get. Integration ax sec theta and tan theta into d theta. Okay, and this anyway x will be coming out. So since it is not a variable, so sec theta tan theta integration will give just sec theta plus some integration constant. All right, anyway, we'll just take the limit after putting the value. So we had r dr, it was. Okay, so this we have got sec theta, x into sec theta, okay, and plus some integration constant. Anyway, so what is sec theta? We had taken x, sorry, r is equal to x tan theta. We have to find out what is sec theta. Then we'll take the limit. So tan theta is equal to r by x. What is tan square theta? So tan square theta will be r square by x square. Now what is sec theta? See, tan square theta, 1 sec square theta, sec square theta is equal to 1 plus tan square theta, right? So we have got, what is tan square theta? So 1 plus r square by x square. So this implies sec theta to be equal to x square plus this will be 1 over x, this. Okay, so 1 plus tan square theta, this implies sec theta is equal to square root of 1 plus this. Okay, all right, so we have got what is sec theta, or this will be 1 over x square root of x square plus r square. Let us see what we had. We had sec theta we had got. Okay, so x is x, and this is so we have got, and obviously we have not put the limit. So we had just taken this as I. So we have finally v of r anyway. So this will be, so this was actually integration r dr by this square root of this, and here it was sigma by 2 epsilon 0, 2 epsilon 0. So this part we had already integrated, so 0 to r integrated, we had already integrated this. So what was the integration part? Result was r square plus x square, and with a limit 0 to capital R. So sigma by 2 epsilon 0, then put the limit when R is small r is capital R. This is actually limit on R. Then it is R square plus X square. When the lower limit is put, lower limit, that is small r is equal to 0. That means it will be X. So this is the value. This is the value of the electric potential due to a disk of radius r. And where we have calculated electric potential at a distance x from the center, and that x is actually, that point is axial point. Okay, as we had shown you in the beginning itself, that was axial point. So this is the electric potential for the disk. Now what we can do, we can see the variation of this value. Okay, we will just get another page. Acha, with position x, with the distance on the x, like in the axis of the, along the axis of the disk, how electric potential vary. Sigma by 2 epsilon 0 here, and this is square root of r square plus x square minus x. So we'll take few limits. Suppose so x is equal to 0. This means electric potential at the center of the disk. At the center of the disk. So what will be that? So that will be sigma by 2 epsilon 0, and x is 0 means this is also 0, this is also 0. So this is the maximum value at the center on the disk. Now if second condition, if suppose x is much greater than r, then what will happen? See what will happen to this. X is much greater than r. So let us take x common. So 1 plus r square by x square, or this, say this, since x is much larger than the r, then this value r by x will be less than equal to 1, right? So this can be now actually expanded according to binomial expansion. Okay, binomial expansion, we can do that. So this we can write x 1 plus r by x square whole to the power half. So this we can write up to first term approximation. We can do is that x whole into x into 1 plus nx. N means r square by x square. Here 2 will be there. Okay. So this is up to first term. Other terms will be further lower. That's why this is x plus r square by 2x. So this will be actually the value of that, and hence electric potential at this particular uh, condition, V will be sigma by 2 epsilon 0 so this was there, and further minus x was there. So what will be the value? This will cancel anyway. So sigma r square by 4 epsilon naught x, q by 4 epsilon naught x. I think pi also will be there. Pi also will be there because, let me check. Okay, so we have sigma, right? We want to write in terms of charge. So pi r square. I hope this will be 4. Sorry, this is all right. This is sigma to sigma. Sigma by 2 epsilon. This we can just multiply pi r square sigma. So 2 pi r square we have multiplied. So 2 pi sigma r cube or q by 2 pi epsilon naught r cube. So this we can write for the center. Okay, the other term let us just take care. So here sigma r square is there. We can just multiply pi in the numerator and pi in the denominator. Okay, this will give you q, and here 4 pi epsilon naught x. Okay, so we can see that this relation is obtained due to a point charge, just like due to a point charge. So what does this mean? That means if you go far and far away from the disk, the whole charge distribution will be considered as a point charge, which is concentrated at the center. Okay, at the center. It is difficult to calculate the potential at the point other than on the axis. It is not so easy to find out electric potential at any point of the disk rather than a point on the axis. So it is difficult to calculate the electric potential at the point other than on the axis. However, potential on the edge of the disk can be calculated. Okay, so electric potential due to edge can be calculated. So that we'll see tomorrow. So tomorrow, what we'll learn? Electric potential. Electric potential at the edge of a uniformly charged disk. Okay, so this will be our next lesson. So thank you for your patience. Bye for today.